Okay, thank you all for coming. My name is Nick Forrington. I'm in the Pro Services team at ARM, and I'm based at Oak Ridge National Lab. I'm going to give you a very brief introduction to ARM Forge, our cross-platform development tools. So just to put this into context, ARM provide the following for their ARM architecture support. So as part of this, we have ARM Forge, our cross-platform tools, which I'll be talking about more. But in addition to that, on the ARM architecture, we also have the ARM compiler for Linux, and that's bundled with performance libraries to accelerate things like LAPACK, BLAST functions, FFTs, and things like that. And so on the ARM platform, these are bundled together into what we call the ARM Linear Studio. Well, as I said, today we're focusing solely on the cross-platform tools. So we have ARM Forge. This is the de facto standard on a lot of the large HPC sites. So where I'm based at Oak Ridge, we have this on the Summit machine. It's very scalable. This will scale up to the full size of the machine and let you profile and debug your applications. In addition to being scalable, in terms of the size and speed, we leverage a tree-based architecture, so this allows us to execute quickly and also to aggregate data scalably as we move that up to present it in the graphical user interface. We support a number of different parallel programming paradigms, so OpenMP, obviously one of them. We also do MPI, CUDA, various others as well. And crucially, we also support HPC workflows. So we have a remote client that will help you connect to a remote system, so you don't need to rely on X11 forwarding, which can be very slow when you're remote. And we also support running inside batch systems, and so this works both for profiling, as you might expect, but also we have an offline mode for debugging as well. So just a quick overview of what's new in the last couple of releases with Forge. So 19.1 is the one that's out right now. 20.0 will be out at the end of this week for the supercomputing release. So a few of the features we've got there, Python profiling was added recently to MAP. We've added support for Lawrence Livermore's Caliper project, so we can add those regions to be displayed in MAP as well. Memory debugging features in DDT have been enhanced to cover NVRAM. And the big item for supercomputing this show is the CUDA on ARM support. So NVIDIA have just announced that they're bringing their stack over to the ARM platform, and so our tools are now ready to support that. The picture on the right there is an image of our configurable metrics feature, which is new in MAP. So you can choose individual Linux perf metrics to profile along with the rest of your application. And we've also added an assembly view to DVT. So I'll start out with a very quick overview of DDT. A quick display of how you prepare your application. Essentially, you compile with debug info, disable optimizations to stop your application jumping around too much, and we aim to make this as easy to launch as possible. So a couple of example command lines there. We can do DDT connect, which will actually launch from inside a batch system and connect to an external GUI that you've already connected. So that's our remote client, and that will pop up a little box like you see in the top right there, which tells you that a request is available. You can click accept there, and that will connect the batch system into your GUI. And at the bottom here is an offline view, which is running at near the full scale of Summit. So that's about 25,000 threads there. This was 4,096 nodes. So this is something that obviously takes a while to go through the batch system. And so it's nice to be able to do that kind of debugging non-interactively rather than having to be sat in front of the computer when the batch system fulfills your job. So here's essentially a screenshot of the DDT session once it's launched. You can see up in the top left here, the blue bar represents the current process group. So in this case, we have 4 processes. Just above that, we can see what the current focus is. So at the minute, we have focus on group. So most actions that you perform will apply to the whole process group. You can also switch that to focusing on an individual process. So again, only focusing on an individual process, and you can also drill down to the thread level where you control one thread in isolation. So as well as affecting things like step operations and adding breakpoints and things like that, we can also see this reflected in the parallel stack view, which is in the bottom left here. So as I mentioned the tree earlier and the data aggregation, so when we collect stacks for all of the individual processes, we merge these going up the tree, and so in this case we can kind of see a tree-like stack view where on the left we have counts of individual processes and threads that are at this particular line of code. We can also see over on the right we have local variables, so as well as displaying the values for the current thread, we also have individual highlighting there, so the green in this case represents a value is not the same across all processes, so that's something that we just collect automatically to kind of point out to the user in case that's relevant for them. You can also see these little graphs or little graphics next to all of the variables. That's essentially a little graph of the values of all of the value of the variable across all of the individual either processes or threads, depending on how that's configured. So if I step that on one, this is essentially what the same view looks like. If I focus on an individual process, I can see all of my individual threads now in the top left. And then also in the stacks view, we can now see that this is also filtered down to display only threads from the current process. And then also focusing on threads as well. So we also have an ability to compare values across individual processes or threads. So in this case, this is essentially a version of the last screenshot where I've stepped one of the individual threads past a point where this W variable is initialized, and so now we can see at a glance that thread 1 has a non-zero value for this, whereas all the other threads still have a 0 value. So I'm going to move on quickly to map now. So map's a sample-based profiler, so that enables us to keep the overhead low. The sampling rate is adaptive as well, so for particularly long-running jobs, essentially the sampling rate will be, or the sampling interval will be increased, so we collect less data as the job goes on, and we kind of consolidate this data as well. So the idea is that your profile will be roughly the same size no matter how long your job is. So you don't have to worry about things like exhausting the file system or excessive overhead as you have longer jobs. We aim for this to be easy to set up as well. So this is a case of adding -G to your program before you profile. There's no compiler wrappers or any kind of instrumentation or anything like that to do. And there's a quick example there of how you might collect a profile there with 10 OpenMP threads and integrating with your existing MPI launch. And again, using the remote client that we mentioned before, you can display that within your laptop. So here's a quick look at what a map profile looks like. You can see along the top where we have the application activity. Going left to right is time in your program, and then vertically is the number of processing elements you have. So we can see the different colors represent different types of activity. So these can be seen in this kind of key along the bottom here. So in this case, the average of all of these is we have about 50% OpenMP. We have around 17% MPI. We're displaying file I/O there as well, and potentially interesting for OpenMP as well as we display OpenMP overhead. So that's essentially the amount of time where threads are waiting for other threads to finish an OpenMP region. So this can potentially indicate some kind of workload imbalance or something like that. Below that we can see metric graphs, so you can actually toggle these out for different metrics. At the minute we're showing cycles per instruction and how that varies across the job, and also memory usage. And so these are aggregated across all of your processing elements, so this could be processes or threads. We have the source code view in the middle here. You can see kind of in the left-hand side of the source view, there's kind of a decomposed version of the activity timeline up there. So this is the activity timeline as it applies just to this line of code. You can also do things like if you collapse a particular loop here, then you will see that that graphic update to apply to the whole loop. So this can be useful. And then the parallel stack view at the bottom here, this shows kind of your profile, where your application's spending all of its time. In this case, we've got most of the time spent in perform time step. If we were to expand this here, we'd be able to drill down and see a little bit more detail there. We can also see in this particular example that we're spending about 20% of the time in an output function, and we can also see the decomposed activity there. So we can see within output we've got a lot of MPI communication, various little bits of I/O in there as well. And so as a very kind of first step into looking at this profile, you might want to wonder why this particular application is spending about 20% of its time just outputting data. So yeah, a good next step here would be to expand that down and dig into exactly what's going on within that function. So here's just yeah, kind of a zoomed in version of that. You can see again these activity timelines are all kind of decomposed here, as well as viewing applications by stack. For OpenMP as well, we also identify individual OpenMP regions, so you can expand in the same way via these regions. Again, we have the activity here. We can see inside the OpenMP regions we have a lot more green, which represents compute, rather than some of the MPI in the other views. We can see the name of the OpenMP region here as well. This is generated by the compiler, so you know, the name there can vary. And we have a little kind of preview of what the source code looks like there as well. So as we support OpenMP as well, we support CUDA. And so if you have an OpenMP offload compiler that generates CUDA kernels on NVIDIA hardware, we can also display some GPU information there. So you can see in the timeline along the top now, there's a lot more purple introduced, which represents the time the CPU is waiting on the accelerator to do something. So a lot of time in there, kind of waiting for the accelerator. Again, this filters down to the stacks view, and an additional view we have for GPUs as well is the kernels view, which we have in the bottom right there. So similar to the OpenMP regions that we had before, you can see compiler-generated names there. And on the left, you can see time spent executing individual kernels. And then quickly onto performance reports. So performance reports, you can create this directly as you would collect a map profile. Another interesting thing to do as well is you can take an existing map file and convert that over into performance reports. What that aims to do is give you kind of a one-page report summary of your application. And so you can see things like system load and GPU usage in here. In this particular example, this is a performance report of the individual, the OpenMP run without GPUs that we were looking at before. So this is going to break it down, telling us that we're spending this much time in compute versus MPI and I/O. And then this is all in the same report, but if you were to scroll down, you would see individual sections that have a little bit more information. So from an OpenMP point of view, the interesting sections here in the top left here, we can see that 98% of the time is within some kind of OpenMP region. We have different information on MPI, I/O, things like that. If we go into the OpenMP section as well, we can see things like the breakdown of computation versus synchronization here. So again, this is the synchronization here. This represents time where you have OpenMP threads that are essentially sitting idle, waiting for others to finish the regions. And so a high number here will potentially indicate you might have some kind of workload imbalance to address. And if you look at all the individual sections as well, then this includes kind of advice that you might want to follow to try and address some potential issues here. So that's my very brief whirlwind tour of the different components of Forge. You can come and see us at the booth if you want to find out more information. If you go to the website there as well, you can also grab like the remote clients, grab an evaluation license, the downloads, and things like that. So be happy to take any questions. Thanks. Which one?